Welcome! In today's lecture, we will derive the dispersion relation of light waves in an unmagnetized plasma using the same technique presented in previous lectures by Professor Ricci. With a two-fluid model, we will define an equilibrium and look for a small perturbation in the form of a wave-like solution. We will study in some detail how the plasma behaves, and we will calculate the index of refraction, the phase, and group velocity of the wave. Finally, we will introduce the cutoff frequency for the light waves and the critical density, and consider a simple model for the propagation of light in the ionosphere. First of all, we write the equilibrium for the plasma. The plasma is overall neutral, and to simplify the problem, we consider only two species, the electrons and one ion species. The plasma is at rest and is cold. So for both species, the equilibrium velocity and the equilibrium temperature will be zero. Then we write the neutrality condition for a homogeneous plasma. This means that for both electron and ions, the density is constant and the total charge density is zero. In such a plasma, there is no electric field at equilibrium. Finally, the plasma is unmagnetized, so there is no equilibrium magnetic field. This plasma behaves as an isotropic system. This means that we only have one solution for the electromagnetic wave, that is the analogous of the ordinary mode in a magnetized plasma. We can now write Maxwell equations. For an electromagnetic wave, we need both Faraday's law and Maxwell-Ampere equation. J, the current here, is the global current for the two-fluid system, and it can be expressed in terms of the electron and ion density and velocities. As we will see a posteriori, these are high-frequency waves. That is, their typical oscillation frequency is of the same order or larger of the electron plasma frequency. In this situation, since the mass of the ions is much larger than the electron mass, this wave propagates on such fast time scales that the ions do not have time to move, and they can be considered as an immobile neutralizing background. For this reason, the density of the ion and the velocity stays constant all the time and equal to the initial value. In this situation, we can write again the current that now will just be a function of the electron density and the electron velocity. In order to describe the propagation of the waves, we now need to write the equations for the evolution of the electron density and the electron velocity. This is given by the fluid equation. First of all, continuity equation. That is also conservation of particles, and then the momentum conservation equation. In this equation, since the electrons behave as a charged fluid responding to electromagnetic fields and pressure fields, we have a pressure term. However, in our case, we consider a cold plasma, and we can neglect this term. We can now consider a small perturbation and linearize our equations, the fluid equations and the Maxwell equations. At the same time, we will take the Fourier transform as we have seen in previous lecture by Professor Ricci. First of all, we define a small perturbation and the Fourier transform for the electron density. So the perturbation is much less than the equilibrium quantity, and the Fourier transform is defined in this way. We can do the same thing for the velocity, the electric field, and the magnetic field. However, all these quantities are zero at equilibrium. So we'll simply have, and so when you will see a tilde sign, like here, on top of U, E, or B, you will know that we are now considering the Fourier transform of these quantities. We can now write Maxwell equations for the Fourier transform quantities. Then we can write and linearize the fluid equation for the Fourier transform of the electron density and velocity. So this is continuity equation, linearized. And this is the momentum conservation equation, linearized. We have now as many equations as unknowns, one scalar and three vectors. We can then solve this system. To do so, we will express the velocity of the electrons as a function of the electric field. Then we can replace this in equation 2. Equation 2 now becomes now we can deduce a number of properties. First of all, from equation 1, we can deduce that the electric field and the magnetic field are perpendicular, and also the magnetic field and the k vector are perpendicular. From equation 2' that we just wrote, we can deduce that the electric field is also perpendicular to the k vector. This means that inside the plasma, an electromagnetic wave still consists of a triad of orthogonal vectors, as in vacuum. So it's a purely transverse wave propagating inside the plasma. On top of this, from equation 4', we can see that the velocity of the electron is parallel to the electric field. This means that the velocity of the electron is also orthogonal to the k vector, and u dot k is 0. From this, from equation 3, we can deduce that the density perturbation is also 0. This means that while the wave propagates in the plasma, there is no motion of the electron density, and the electrons just move as rigid plane up and down along the electric field. In this slide, we can summarize what we just learned about an electromagnetic wave propagating inside the plasma. What is shown here is the electric field together with the electron velocity as a function of space and time. In the last line, you can see planes of electron oscillating up and down according to the electric field. The movement of oscillation is characterized by a typical velocity that is called the oscillation's velocity, that is defined here, is the absolute value of the velocity of the electron. The maximum value that it can take is the oscillation velocity, and is given by the charge times the electric field over the mass times the frequency. We have found that the electromagnetic wave is a purely transverse wave, as in vacuum, and we have seen how the electrons behave when the wave propagates. Now we still need to find the dispersion relation of this wave in the plasma, that is, how the frequency is related to the wave vector k. To do this, let us define the plasma frequency that you have already seen in previous lectures. By using this definition and by combining equation 1 and equation 2', we can write an equation for the electric field only. Since, as we have seen, the electric field is perpendicular to the wave vector, we can simplify this product, and we just have where now k is the absolute value of the k vector. If we use this condition, the equation becomes simply this equation can be satisfied only if the right-hand side and the left-hand side are identical, and this leads to the dispersion relation. As we can see, these waves are indeed high-frequency waves, since the frequency is always larger than the plasma frequency. So the hypothesis of considering the ion as immobile is justified a posteriori. This dispersion relation is plotted here, where we show omega as a function of k, so the frequency is always larger than the plasma frequency, and when the k vector is large, so this term is dominant, or if the plasma frequency is very weak, we have that this dispersion relation asymptotically is equal to the dispersion relation of light in vacuum, as one could expect. We can now solve for k as a function of omega, where k is a real quantity only if omega is larger than omega p. However, we can still find a solution for k even in the opposite limit, but in this case, k will be purely imaginary. And the imaginary contribution is equal to. We will discuss later the meaning of this solution, and for the moment we just focus on the previous case, that is on the case omega larger than omega p, and k real, that is the case of a propagating wave. We are now in a position of calculating a number of quantities that are related to the electromagnetic wave in the plasma. just for the case omega larger than omega p, that is a propagating wave, we can calculate first of all the phase velocity. The definition of phase velocity is omega over k, that is, by the dispersion relation. Since omega is larger than omega square, the denominator will be less than 1, and the phase velocity is larger than the velocity of light. We can also calculate the index of refraction, that is defined as the velocity of light over the phase velocity. And in this case, as opposed to the index of refraction in materials like water or glass, the index of velocity of waves in a plasma will be less than 1. The condition that phase velocity is larger than c should not worry you, because it's not really a violation of relativity. In fact, transport of energy or information, they are not associated with phase velocity, but with group velocity. So even if the phase velocity is larger than c, the system is still a physical system and well behaved. However, if we calculate the group velocity, that is defined as the omega over the k, and for light wave in a plasma is equal to c square over v phase, or c times the index of refraction, we see immediately that this quantity is well behaved and less than the velocity of light. We can now consider what happens when a wave propagates from air to a plasma. So this is air, and this is the plasma. We can apply Snell's law, and we will have that going from air to the plasma, the refraction angle is larger than the incoming angle, as opposite to what happens when light goes from air to glass or air to water. Since the index of refraction of a plasma is less than 1, this implies some peculiar behavior for optical objects. This is the normal to the surface, and the wave would be refracted further away from the normal. Let us now go back to the dispersion relation. If the frequency is below the plasma frequency, as we have seen, there can be no propagation and k becomes purely imaginary. An imaginary k means that the wave becomes evanescent, and it will only exist and penetrate in the plasma up to a small length that is called the skin depth length. This length is equal to the inverse of the imaginary k. And if the frequency is much less than the plasma frequency, is given by this simple formula that you might have already crossed. We are now in a position to define the cutoff frequency for light waves. This concept of cutoff frequency was already introduced by Professor Ricci. So what does it mean? In fact, if we have a frequency such that for this frequency the wave vector k is equal to 0 and the index of refraction is also equal to 0, this is called the cutoff frequency. For light wave, this happens for omega equals omega p, the plasma frequency. And this frequency gives the cutoff between a propagating wave and the wave that becomes evanescent at the plasma surface. What happens, in fact, when the frequency is below the plasma frequency? The wave is reflected. So here on the right we have an example of a simulation where a wave packet is impinging on a plasma, and the plasma is chosen such that its plasma frequency is above the cutoff frequency for the pulse. As you can see, the light gets in and then it starts to be reflected. It's fully reflected and leaves the plasma, and the plasma stays unchanged. While the light interacts with the plasma, it will penetrate a little bit in the evanescent length that is, however, very small and is barely visible in this simulation. A nice example that you are all familiar with, that is related to the fact that a cutoff frequency exists for light wave in a plasma, is the fact that the metals shine. The free electrons in the conduction band of the metal, in fact, can be treated as a cold plasma, and then we can calculate a plasma frequency associated to that. If we now consider the pulsation of visible light, it is between 2.7 and 4.8 10⁻15 rad per second. So we can see that all visible light is below the plasma frequency of the conducting electron, and for this reason all visible light is reflected, making metals shine. We can now look at the problem from another point of view. In fact, we can consider a given frequency, omega 0, and this frequency will be able, a wave with this frequency will be able to propagate in a plasma only if the density is below a critical value that is such that the plasma frequency is equal to this frequency. We can thus define a critical density that is such that if the density is below this critical value, there is propagation. If the density is above this critical value, there is reflection. The critical value is the value of the density for which the plasma frequency is equal to the frequency of the considered wave, and is then given by this formula. The notion of critical density is very useful if we consider that the plasma density is not homogeneous. So what I'm showing here is a density profiles that evolves with space. The equilibrium density is a function of space, and for example, it has a shape like that. Now I can consider an incoming wave that is propagating in the same direction of the density profile. For example, can be something like that. The light will propagate in the plasma, and during the propagation it will keep its frequency constant, but instead the plasma frequency will vary as the density increases, and then the plasma frequency increases. This means that the light can only propagate up to the point when its frequency is below the plasma frequency, and this is the critical density. So, for example, let's say that this point here corresponds to the critical density. With this configuration, light will propagate up to the critical layer, and then it will be reflected. We will discuss in the next lecture what happens when light, instead of propagating parallel to the density gradient, propagates at an angle, oblique incidence. As we will see, the situation is a little bit different. Finally, we can introduce a definition that you've already seen in the previous lecture. The part of the plasma where light can propagate is called underdense, and the part of the plasma where light cannot propagate is called overdense. Most of the results that you learned in this lecture are summarized by this video that we can watch together, and then we can discuss. What we show here is a simple model for the ionosphere. The ionosphere is the higher part of the atmosphere that is ionized. In reality, the electron density increases continuously as we go towards the highest layers of the Earth atmosphere, since ionization increases in the higher layers. In this animation, instead, we consider many layers, each at constant density, and such that the density increases as the color gets darker. At the crossing of each layer, so from here, 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 we can apply what we just learned today in homogeneous plasma, and this will give a good example of the propagation of the wave. So let's have a look at the video. We can now discuss the video in more detail. So, as we said, the electron density grows, and the frequency of the wave is unchanged during propagation. However, because of the growth of the density. However, as you have seen in this lecture, the wave vector diminishes according to the dispersion relation of light in plasma. The wavelength that is equal to the inverse of the wave vector will increase, and this is shown in the image. You see that there is an increase of the wavelength going from one layer to the next. The phase velocity increases and the index of refraction diminishes accordingly. The group velocity will also diminish as the density increases. Vg is proportional to n that diminishes the index of refraction. This is not shown in the video, but in fact what will happen is that light will slow down as it reaches the higher level of the ionosphere. Then we can apply Snell's law to deduce the variation of the trajectory. So the impinging angle is increased, and this corresponds to a tilt to the right and gives this trajectory. And finally, in this process, flux is conserved because the wave is just propagating with no absorption. That is negligible in this low-density plasma. So since flux is conserved, this quantity is constant. And since this quantity is constant, given that the group velocity goes with the index of refraction, it means that the electric field will increase as 1 over the index of refraction to the 1/2. And again, you see this in the video where the amplitude of the electric field increases. Finally, when the wave reaches the layer such that the density is above the critical density, the wave is reflected, and the reverse trajectory is done by the wave. We can now summarize what we have learned in this lecture. In order to describe light propagation in a plasma, we can use the two fluids model, but treat the ions as a static neutralizing background. Light can only propagate in a plasma if its frequency is above the plasma frequency. In the opposite case, it will be reflected. If light propagates in an inhomogeneous plasma, the index of refraction decreases as the density increases.